Good evening. We need to hurry up so that my battery doesn't run out before I run out of content. Which leads me to the topic robots. This talk is about what we need to consider when developing rules and regulations for robots and for autonomous systems and other complex technological entities that are not manageable by a normal way of managing risky technology. We start with the three laws thanks, that Asimov stated in his novels. They should be universally known. They say a robot should not harm a human being, either actively or inactively. It should follow orders and it should preserve its existence. These rules are fine as subjects for novels, but they're unfortunately very impractical when it comes to real-world systems. There has been a very nice illustration to that. These rules do not include the option of malicious intent. So no one can, under these rules, develop systems that hold up to malicious users, to malicious builders, to malicious people trying to influence the systems. So we need to conclude robots are risky. So there is no way denying that. When we look at Asimov's laws, they have different statements in them, like injure, harm, what's a human, orders, protect. So there's existence, what's that? So there's no means of knowing for a robot what does it mean to harm a human. So what's the meaning of protect? So is it, I don't know, just standing here? So currently most robotic systems, if they don't know what to do, they just remain standing still. So if you look at, for instance, the videos of the DARPA challenge, which was the big trial out for having automated cars driving around in a simulated urban environment, what they basically did is they had 15 teams and they had automated cars that should fulfill a number of tasks. And they had stunt drivers in actual cars simulating human traffic. And they wanted to show that these cars can drive around in the city without harming too many humans. And actually the number of accidents was surprisingly low compared to 2 years before, when it was a non-urban trial where they drove around the desert near Las Vegas. And so it was relatively cool. So they had these cars full of sensors and everything, trying to drive around. And when these cars were out of options, basically not knowing what the environment was or not being able to conclude what they should do, they were just sitting there waving a red flag and saying, okay, I don't know what to do. So the problem is there's no real artificial intelligence on the horizon. So artificial intelligence is more or less like fusion power. It's always 15 years in the future, always, at any given point in time. So, and it has been that way since the 60s. It's always 15, maybe 20 years until we have real AI. And it will be really cool. But what we have is increasingly complex software. So the systems that we are building today that are running actual machines like industrial components, even normal personal computers or automation systems, semi-autonomous machines that are driving around in factories. The software is getting increasingly complex. It is getting so complex that you're not really doing any systems engineering in a conventional sense on them anymore, but they behave. So if you talk to operators of really complex machinery, they tend to personalize the software that they need to work with. We come to that later in detail. This kind of software caused already death and injury. What we have here is a satellite picture of California in the August 14, 2003. What you see here is California, and it's dark because they had blackouts. And the latest postmortem I have read about it was these blackouts could have been prevented to a large scale if the reliance on automated systems was not so total that the functioning of these systems was taken as a given. In other words, the systems failed and the human operators, the few that remained there, got too much input to parse. So a cascading failure in an energy network is something that no human being can conceivably stop because there are way too many options. So it's the same basically with the nuclear power station. They try to skim down the options that an operator has in a nuclear power station by using multiple automated systems so that he can maybe understand what's happening, but in full-scale power system, that's not possible. Plus, almost all modern software is buggy. And above a certain complexity level, it's not even deterministic anymore. So if you look at what is happening in the field of what's called artificial intelligence in computer science, that's neural networks, that's stuff like motivation-based learning. And these are more or less self-evolving systems. They are not intelligent, but they are not deterministic anymore, and they are not predictable anymore. So you cannot really predict what these things will do in a given situation. You can just have certain convictions about what they should do. And so the point of software is something deterministic, and we can understand what the system does is long past gone. The graphic behind the text here is the Windows 32 call graph for system functions. And who here would think that Windows 32 is a deterministic software? I see no hands. Okay, there is the option of saying these systems could be legal entities. This is actually being debated in the scientific literature, saying if a system has certain characteristics, that it knows about the environment, has rules how to decide about its environment and what it should do or should not do, has something like a computerized moral or ethic framework on what to do and not to do, then it should maybe get the status of a legal entity that earns its own money and is therefore being able to pay its own insurance, which I find a fascinating construct of logic. But the problem is this also doesn't really hold up in reality. So if you have such a system and somebody's building it, it thinks, okay, this is not an entity but a machine that I own. And this is what we're thinking currently. So, but at least it's being discussed. What we have today is not really fully automated robots, but lethally armed remote presence machines. So these things that we have here is a little tank that has a machine gun, a couple of cameras, lots of wireless stuff. It has actors, it can mount an arm, lots of batteries in it. And these things are actually deployed in the battlefields today. So it's not future, it's just the stuff that is from a product catalog that you can actually order as a military today. These things have very, very limited onboard intelligence, but they can theoretically operate beyond visual range. So we're having normally the definition, okay, a remote controlled machine is something that is operating behind there in the corner because I don't want to go near the bomb. But actually what we have today is UAVs that are flying around the world controlled from somewhere in Kentucky. And these things have onboard intelligence that at least makes it possible that they fly to a certain corner of the world and fire a Hellfire missile without somebody having really tight control but saying, okay, go there, okay, looks like a target, fire. So there is a transition from remote presence to autonomous systems. And that's a very fascinating transition. Somebody has written more or less in reply to asimov laws. It's basically saying a robot will not will not attack government personnel, but everybody else. And it will, of course, obey orders. And it's goddamn expensive, so better protect itself. I found these laws actually more realistic than Asimov laws. The author is a British science fiction writer. To get another glimpse of what is happening today, we have here a video from a drone in Iraq that is getting a bit out of control. So now it's in auto land mode, and it's landing. The face of that guy is really priceless. So what we have here is somebody who has really, really high confidence in software. And so that brings us to the very interesting question. So let's assume somebody put on the wrong coordinates and and he would be actually wiping the floor with that guy. Who would be responsible? Is it the maker of the robot, the writer of the software, the guy that happens to be 10 centimeters too tall? So, but these are the questions that we have. So this could be not an industrial robot with some robot engineers having fun, which it is actually in this case, but that could be a piece of entertainment software tied to a physical interaction device. So we're moving into a realm that has increasingly complex questions. If we want to invent regulation or rules, we should define goals. Rule number one, we should try to reduce the number of victims. Of course, we want to save money. Rules and regulations should be developed in practice so that they are actually practical and not just stupid rules that somebody developed on the green board. We want to prevent stupid panics, like robot armies will roll over the streets and eat us all. And we want actually meaningful and realistic regulations. So what could be elements? This is something that is not actually a robot, but a remote-controlled plane. So that plane is also getting a little bit out of control in just a second. And it's not stopping. It's just simply not stopping. So now we imagine that thing landing in a kindergarten. This would cause a stupid panic. Yeah, it's a bit lengthy. Chopping up little lambs. Now it's dead, Jim. So let's take a look at what the current regulations model for risky technology are. There is already lots of risky technology around, so the question is, can we learn something from that? We have the Anglo-Saxon approach. If it can be ensured, it should be okay. Actually, while researching this talk, I learned something. You probably have seen this logo on a lot of PCBs, that one here. Does anybody know what it stands for? It's for a registered part for and recognized part for the Underwriters Laboratory, which is the logo on the left side. The Underwriters Laboratory is basically an entity in the United States that says, okay, we are analyzing electrical and electronic components and see if they are safe. And when we have them analyze them, then they can be insured. And similar models are working in other countries. But this approach is basically only industry-driven. It's basically saying the industry says, if we can determine the risk, we can determine what the rate of insurance is, and then people can decide if they really want to use that system or if the insurance is too high for them, so they won't use it. That's basically the free market approach. Then we have the nuclear approach, which is the state tells you what you can run and how. The reason for that is because nuclear energy stuff most of the times cannot be fully insured. So if you have a nuclear power station going wrong, it's a little bit difficult. So most insurances terminate at 500 million payout. And if a nuclear power station contaminates a whole country, then it's probably a bit more. So that's why there are certain areas of technology where the state actually mandates in a number of states what can be run. And then we have the German approach, the TÜV. And the TÜV is even more fascinating than most of you think. For those of you who are not from Germany. The TÜV has been founded in the age of steam engines. When the first steam engines were installed, they tend to blow up. Actually, they tend to blow up a lot. And it was rather ugly. So, and at some point in time, people tended to say, not in my backyard. And so what happened was that the actual engineers running the steam engines and the engineers building the steam engines were getting together over beer in the evening and were discussing what could be done. And what they came up with was the Dampfkesselüberwachungsverein, which is a really cool German word, and it's meaning the Steam Engine Monitoring Association. And what these associations did was they came up with technical standards how they could make steam engines safe. They were saying, okay, if we have a steam engine and it's new and untested, we want to have certain tests run on it, like using it with double the normal pressure and see if it blows up in a safe area, not in the backyard. Or if we have basically a certain type of steam engine that we have seen before, it's okay if we test it with 1.5 normal pressure, because we don't want to blow up too many machines. And we only want to run steam engines at a certain amount of pressure based on construction data and so on. And we need to make sure that the valves are regularly monitored and serviced, and we need to make sure that only certain grades of steel are used for the steam engine boiler. And we want to make sure there's always enough water in there, and so on and so on. So they came up with a set of very basic regulations. And they found out that actually their employees found it interesting, because finally they had a framework, and follow that framework you could install steam engines also in backyards again. So it was very simple. Basically the technicians were coming up with regulations and rules. They were testing them out, they were discussing them with their peers, so making sure it's not totally stupid. And then they convinced everybody else that it's the way to go. And then something really fascinating happened. It was the time when Germany was unified from very many little states that had all their Dampfkesselüberwachungsvereine into a large German Reich. And along came Otto von Bismarck, who basically instituted these Dampfkesselüberwachungsvereine as the way to regulate risky technology. Basically, if it has a TÜV approval, you can run it. If it has a TÜV approval, you can get insurance for it. Of course, the whole system deteriorated and diluted after a while, so today there's not only one TÜV, but there are many entities that you can basically be a registered entity for regulating such technology with a certain level of expertise and a certain number of engineers and so on. But the basic principle is developing the rules from the bottom up and not designing them at the green table. So if you look at what elements for regulation of robotic systems would be good, this is subject of discussion, so it's not something that I tell you that that's how it is, it's just something that we should think about. The first thing is identification. If you have a remote control system or a semi-autonomous system or fully autonomous system, you really want to know who that thing belongs to. So, of course, if it's a legal entity, it can belong to itself, but still you want to know who it is. So you want to know who's controlling the damn thing and who I need to call when it runs me over, Or, of course, there are easy cases. Like, let's say you are in the Pakistani borderland and something flies above you and fires a Hellfire missile at you. It's probably the CIA owning that thing. So there's not much doubt about that. But there are other cases that are not as easy. So identification is something that is very well ingrained also in cars. For instance, cars have license plates. And these license plates make sure that you can identify this car has done something wrong. It ran me over, or it had an accident, or whatever. And so there is a sense of attribution and a sense of responsibility that can be, of course, it has loopholes and is imperfect and everything, but at least it's a system. The second thing is insurance. Insurance for robots will be the hot topic of the whole thing, because, of course, the first impulse of the industry is saying, yeah, let's insure this shit and then we ship it. So it's not compile, ship it, it's compile, insure, ship it in the future. And so the insurance companies will more or less in the beginning have the power to make or break robotic and automated systems, because if things cannot be insured because they're deemed too risky, then they cannot be shipped. So we have the interesting case at the moment for UAVs, the little drones that the motor drone people are building. If we want to fly such a thing to take pictures in the US, there's only one insurance company at the moment that is insuring that thing. All the others are just sitting there saying, yeah, let's watch how many risks are associated with that. So if that falls into a power line, or if that falls into a car, or if it falls down and kills somebody, or even if they take non-appropriate pictures with that thing, is there an insurance risk? The question is, it can get very complicated. For instance, if you look at Japan, they will have healthcare robots there. We're seeing a few examples later on. So robots that help you in your home, these things are too expensive to buy. So they will be in the region of $100K. So the only thing to get them into the market is rent them out. And say, okay, this is the robot, you pay, I don't know, $150 a month, and you can use that thing. And so who is responsible now for anything that's going wrong with that robot? Is it the person who rents the robot? It's the person who rents out the robot? Is it the manufacturer? Is it the sub-manufacturer of some part? Is it the manufacturer of the software? This whole thing has a higher complexity than a car. At the moment for cars, it's quite simple. So if your car breaks down, you go to the manufacturer, have a warranty. But even there, it's already complex enough. So for instance, Volvo had an incident where the brakes were failing on a certain line of cars, and there were a number of deaths. And it took them, I don't know, I think 11 years until the court procedures were finally done, and it was determined that Volvo was really guilty of the whole thing. And you can imagine how complex that gets with robots once they start interacting with humans. Of course, there's another way to do the insurance thing.
Anne's husband passed away. The insurance company said his policy didn't cover them.
They had no money to pay for the funeral. It's so hard nowadays with all the gangs and rap music. What about robots?
Oh, they're everywhere.
I don't even know why the scientists make them. Darren and I have a policy with Old Glory Insurance that covers us in case we're attacked by robots.
An insurance policy with a robot plan?
Mm-hmm.
Well, certainly I'm too old.
Old Glory covers anyone over the age of 50 against robot attack, regardless of current health.
I'm Sam Waterston of the popular TV series Law & Order. As a senior citizen, you're probably aware of the threat robots pose. Robots are everywhere, and they eat old people's medicine for fuel. Well, now there's a company that offers coverage against the unfortunate event of a robot attack. Old Glory Insurance. Old Glory will cover you with no health checkup or age consideration. You need to feel safe. And that's harder and harder to do nowadays because robots may strike at any time. And when they grab you with those metal claws, you can't break free because they're made of metal and robots are strong. Now, for only $4 a month, you can achieve peace of mind in a world full of crime and robots with Old Glory Insurance.
Robots! They're coming! Robots!
Oh, it's a friendly robot. This time.
So don't cower under your Afghan any longer. Make a choice. Old Glory Insurance. For when the metal ones decide to come for you. And they will.
So we see insurance is a fascinating topic. Okay, if we come to responsibility, how do we define if someone or something is responsible for something? There's a huge debate on that in literature, but in general, it implies you can be responsible if you understand what's happening, if you have a system and you can in reasonable terms predict what it will do. Like, I have this car, I step on the brake, the car stops. I step on the gas, the car drives. I turn the wheel, and it goes roughly in the direction I intend. So you're responsible for driving that car. If you don't have that, because the system is not transparent and not deterministic, if it behaves more like, let's say, a pet, a dog, or your little tiger, or whatever, then it's getting harder. So then there's the added element of surprise, you cannot really predict, and robots will be like that. So robotic systems will not be having a will or a soul or something like that, but they will be driven by complex software that is not really predictable. So if you have an Aibo, Sony, this little Sony plastic dog, these things could get rather unpredictable. And you can develop software for them that makes them really unpredictable. So there have been experiments of motivational learning on them, where the people who developed the software could not really say what these things were interested in. So if you look at the whole domain, we have, with all kinds of technology, we have this interesting gray area. That's that one here. So if we transpose that again to cars or to vehicles, we have the controlled area, which is cars that have above a certain grade of kind of motor, and it can go above a certain speed and have a certain weight. It's relatively simple. It's just a function of power. These are controlled. You can only drive them on roads when they have insurance and all the other things. You have the illegal cars, so stuff that are plain illegal, and then there's the gray area. With robots, it will be the same thing. So when we say responsibility means maybe man in the loop, that's how the military does it at the moment. So they say the final fire command is being given by a human. The robot doesn't fire itself. Then the human is basically a button pusher. So the machine is the button, he presses, it fires. But things evolve. So for instance, in modern military airplanes, you have already automated targeting systems that suggest targets to you. Because the computer is much faster, it has better image recognition capabilities, it can fuse in the radar signals, it can basically do a lot more things than a human can do at one time, and it suggests the most juicy target to you. Of course, it is left to you to press the button, but the target itself, the choosing of the target, is getting more and more automated. And the next step is then, of course, the thing develops into an entity. It becomes an it gets names. It has certain characteristics that you implicitly associate with it, and you're becoming a partner to that thing. So not pressing the button anymore, but you're talking with Linda, and Linda is your flight control system. So there has been some work on how that will evolve. So it starts with manual control. It evolves further to action support, meaning the automated system is offering you alternatives. You choose from a given set of paths that you can have. It can go to decision support, meaning that you're not doing the actual action anymore, but you just have these suggestions and say, do this. It goes further to blended decision making, basically what you have today in power control systems. The system actually decides for you, and you just have the right to veto. So if the system does something entirely stupid, you can push the red button. but that's it. Otherwise, it's left to its own devices. You're going onto automatic decision making. Basically, the system does it, like with stock trading systems, and it just informs you what it has done. And it goes on to full auto where the system basically ignores you. We are not there yet in most systems, but it's coming because it's more efficient. You can do so much more things with automation because machines can input much more sensor data and much more decision-making points and can have much more complex models that you simply cannot compute in your head. And there are other models, for instance, like I was told yesterday, a very fascinating thing. A system to control in a case of large-scale natural disasters where the fire engines are sent. You can, of course, model that. You can model, okay, it makes, if you have large-scale, let's say you have the Bay Area and you have 600 burning fires in a given area. Where do you send your 50 fire engines? So, of course, you can model that and have a software system that does the decision for you. It would probably be more efficient, but it doesn't feel good. So what they do is they use the software to train the humans. So they basically have a very complex system that is being broken down to a level that the humans can already understand and understand the rules that the system is following. And then the humans acknowledge what the software would do anyway. Another very fascinating thing is that the more automated the system gets, the more personified it gets. So people regard things above a certain complexity as person, pet, whatever. So then we have, of course, the survival of the cutest, not only in the animal kingdom, where you have the fact that the more cuter and cuddlier an animal is, the more TV time it gets, and the more higher its chances of survival are. Cuter animal races have a higher chance of survival. And with robots, it's basically the same thing. So they are made looking cute because it's not looking so harmful, and so, yeah, and you have this very little nice green dishwashing thing, and it also can be adapted to cultural. This is the. This is actually a battlefield extraction robot that has been designed to get people out of battle zones. And of course it looks cute because when you're shell shocked, then you don't want to have some ugly Terminator going over you and ask. So our new metal overlords will look cute. So that's for sure. Okay, what other safety measures we want in self-learning systems? In very interesting, despite identification and insurance and stuff like that, an interesting suggestion was having something like a flight recorder. Basically, in tamper-proof memory that records as many data points as possible about the system so that you can at least afterwards look if somebody fed that thing malicious input, like trained it to be evil, which is not unrealistic, or what actually happened so that you can fix that thing. But then again, the question of responsibility. When you have a self-learning system that has its own motivation matrix, it has a neural network that can only roughly be predicted, who is responsible for that thing? Is it the manufacturer? Or is it the owner? Because the owner can train that thing. We are back to the basically to the dog question. So if you have a very aggressive dog, and you know that there are a lot of these dogs that have attacked humans in the past, then you tend to assume that you need to be more careful with that thing. But of course, you can train that dog to be the most peaceful dog of all, or you can train it to be the most evil dog of all. Who's responsible? Is it the breeder? Is it the owner? We tend to assume it's the owner. So because he has final responsibility. But what if he bought that dog only a few days ago, or that robot? Or if he got a software update for his robot dog that made that thing suddenly evil because he didn't know. And so the field of complexities that are opening up are really endless. And we currently don't have any means of developing regulations and rules for that. So we have a very high dynamic of development. The basic technology is evolving very fast. Software is developing as fast as people can type code. Formal methods and formal certifications are being done in the field, for instance, for industrial robots that are moving car parts around in factories and so on. There is movement in the universities to have formal verification methods, basically trying to run these systems fully deterministic and have the self-learning done before, basically in the lab, and move a static but evolved system into the field that you're reasonably sure what it probably will do. But it slows down things a lot. So it's not the dynamic of software development anymore, but it's more like car manufacturing where you have 7 to 8 years development horizon. So cars, if you want to buy a car today, it has been developed 7 years ago, if it is factory fresh. And since we are at the cross-section of so many areas of knowledge, so there's the whole robots and autonomous systems thing is really colorful. So you have the artificial intelligence people that still dream of having HAL 9000, controlling their dishwasher. And you have, on the other hand, the people who say, okay, let's get down to earth. I just want to have a car that drives me home when I'm drunk. So, which is probably a more realistic approach. So for instance, the car manufacturers, where we are at assisted driving, the car manufacturers have a very fascinating argument against assisted driving. They say nobody wants it. Because people love to drive cars. I was really astonished by that because I thought, okay, what could be more perfect than a car that I just tell where I want to go and it takes me there? But apparently, no, that's not the case. People who buy the real expensive cars where these automated systems would go in first are the people who really love to drive cars. So that means the driving assistance modules like keeping your lane, brake assistance, steering assistance, collision avoidance, stuff like that, it's phased in very, very, very slowly. So in principle, we are, I don't know, maybe 3 or 5 years away from a production-ready car that could drive you home without making too many accidents. But the question is, who would buy it? Who would buy here a car that would just drive you home? Okay, you nerds. Okay. Here's something that I want to discuss. The question is, we are all going to somehow have to do with robots. We tinker with them, we modify the software, we have them cleaning our carpet. It's getting increasingly into our lives. And of course, we will mod these things. So building the hardware is expensive and takes long, but once you have that thing on your desk, of course, the first impulse is rip it open, look at the software, modify the software. This is, of course, what everybody here would do. So, which has a number of risks. And in order to contain these risks, we should think about what to do. And the idea that I came up with and I want to discuss, I discussed already with the people building these little UAVs, the micro drones, and they found it interesting, and I also want to discuss it in a more general area, is putting something like the original TÜV, you know, the Dampfkessel-Überwachungsverein, make that for robots, peer-to-peer. The principles is very simple. So if you do build something that has physical impact, find a competent peer that can look at it. Basically someone who can understand what you have done and tell you, okay, do we have an emergency off button? What does that thing do if it, I don't know, catches a cable, or if it runs out of power, or what does it do in that situation? And also, if you're competent enough, then volunteer to be that peer to somebody else. So the whole concept has been developed, of course, in the open source software community. The problem there is, since it had never been, there has never been a formal method to that, we have the open source problems that we have today. Nobody's reading the source anyway. And everybody's just copy-pasting source from somebody else that he doesn't fully understand and hopes it works in the end. So if you look at this open source software quality that we have today, it is not what it could be, by far not. Which is fine and okay as long as it only crashes your web server. But if it comes crashing down your front door, it's something different. So that's why I would like to discuss something to make it a bit more formal, to at least institute something that is in code of ethics for engineers that says, if you're building a system or modifying a system that can have physical impact on other people or other people's property, then at least have somebody else look at it, and look at it in a way that is a bit formal. So the typical thing that will happen there is you have the basic check like, okay, I built this thing, or I modified it, or I wrote this operating system for carpet cleaning robots, or I modified this bread buying robot to rob banks. And I just want to make sure nobody gets killed in the way. So can you please look at it? And then somebody else will come, a good friend probably, who built his own bank robbing robot and says, yeah, okay, yeah, but what if somebody with a wheelchair is in a bank? Or what is, if there is a stair and that thing is running down somebody the stairs or whatever? So all the most important questions. And if you change something, you want to have a change check. So he looks at it, he knows the basic system by then, hopefully, at least a bit. And you changed something important, and he says, okay, let's look at it and go over it again. And so the main principle is think about what will happen and have somebody else look at it. So if we look at it from a more general perspective, what we want to have is we want to have safety. These things should not run people over. What you also want to have is ethics. Robots can be made pretty evil without harming people physically. It's very, very simple, even today, to build a robot that is following people around. It's not really difficult. So it's within the realm of today's technology. It maybe the thing runs out of battery after 30 minutes, but in principle it's possible. So you can have surveillance robots that run after you. And you can have plenty of very little surveillance robots that monitor your every move without you even knowing. So the ethics of robot building can get pretty complex. And I want to encourage thinking about it. So is that what you're building at home in your garage or what you're building at work? Is it really okay? Is that something that you want to live with in the same city? Or is it something that is rather not so PC? What we also want to do is we want to conserve the right to tinker. So as we had before, there is the risk of stupid panics. So there is the risk that people will freak out because of some accident. So if let's say, one of the microdrones crashes really in a kindergarten, what happens? To prevent that, we need something that is looking good and works in practice. So that we can point to that, say, okay, we have this set of rules, we follow these rules, they may not be perfect, but at least they are rules. If something goes wrong, we learn from it and modify them and end up with the self-iteration, with the iteration that improves the whole system. So if we look at the elements, we need public documentation, basically document what you do. Checklists for known problems, so thinking about what could possibly go wrong, what is the maximum damage that could occur. So if you're flying a microdrone only in your living room here, okay, it's maybe your cat may get shredded, or I don't know, who lives with you may get harmed, or the TV may get broken, which is kind of acceptable. If you're flying that thing outside, it's a completely different story. If you fly that thing outside of your visual range, and it's flying fully autonomous, it's really another different story. Also, we need to learn what has happened somewhere. So is there something that has happened in a similar way? So postmortems are the most interesting things to read. That's actually, there's an interesting parallel to that. It's the experimental airplane community. Experimental airplanes are airplanes that are at least 51% built by the pilot itself. That's the rule. So if you want to build an airplane for you, that's fine. You can do that. If you crash with that thing, it's more or less your problem unless you damage somebody else. And these people did the same thing. They have basically certified mechanics that have learned a lot and that volunteer to look at your airplane before you start to fly it, or if you design the airplane, to look at your basic design and start to talk with you about, okay, maybe the brakes are not good or the flaps are not good or whatever. So we need the same kind of process, only more advanced. As I said, postmortem analysis in airplane building, they say every single rule in these airplane building manuals is written with blood, literally. We hope to avoid it, so sweat would be enough, it must not be blood. Okay, so of course we have the internet. We can set up a wiki, set up a mailing list for that. We will have talks and reports. I'm not yet at the point where I can say, okay, this is the website, let's go, let's do it. So we will do some work at Motodrone, where we have these little flying quadrocopters. We're doing similar work in the area of electrical driven bicycles, which is basically the same thing. We have now powerful lithium batteries, we have motors that are really big, we have efficient motor controllers, and we can build bicycles that go 50 kilometers per hour without you doing anything, which is kind of risky, which we probably shouldn't do. So, but what's the process of getting there that we cannot go at least 25 safely? So, and we're trying to do the same kind of process there, basically exchanging information, finding out what went wrong, exchanging blueprints, keeping it as open as possible. Okay, that's basically the end of my talk. I'm even in time, wow. I'm open for discussion and questions, thanks.
Why is this one? This one's working as well. Any questions? Right.
Thank you. I was wondering, while researching that, if you found out if, for example, US military or any other entity is producing such autonomous systems like the UAVs and stuff, are they discussing the ethics and safety things publicly?
There is, as far as I know, I found 3 research groups in the military context that are trying to build rule sets for robots that basically incorporate the rules of war, basically don't shoot prisoners, stuff like that. And they're thinking about it under a number of aspects. One of them is not letting the robots run out of control and building systems in that they can basically run without getting too much bad press.
But also more under the can it be insured context.
Yeah.
Any more questions? Okay.
Okay, then thanks.
All right, thanks a lot.